Hello everyone. I, Professor Neha Dikshit, going to explain you next part of hydrodynamic loop. In this part, we are going to see design consideration in finite length hydrodynamic journal bearing, design variables and performance variables, dimensionless parameter, and Remodian point method. Learner will be able to explain design and performance variable, summarize dimensionless parameter, explain remedy and Boyd method. First of all, we will see design consideration in finite length hydrodynamic journal bearing. Variables in design of hydrodynamic journal bearings are classified again two types of variable, design variables and performance variable. First of all, we will see design variables. Design variables are those whose values are either given or under the control of the designer. For example, journal speed, viscosity, unit bearing pressure or load per unit projected area, bearing dimensions that is radius, clearance, length and arc of a bearing that is beta. When these four variables are defined or selected, design of bearing written. Next variables are performance variables. Performance variables are those which tell us how well the bearing is performing. Performance variables are coefficient of friction, small f, temperature rise delta T, flow rate of lubricant capital Q, and minimum oil film thickness HO. The designer cannot control these variables except indirectly by changing one or more of the design variables. In order to ensure the satisfactory performance of the bearing, the values of a performance variable must be within the specific limit. We will see now design of a hydrodynamic journal bearing. Basically, design of a hydrodynamic journal bearing is nothing but defining satisfactory limits for the performance variables and then deciding the value of design variables such that the performance variable do not exceed the defined limits. So basically, for design of a hydrodynamic journal bearing, you have to define performance variables limit and then according to that limit you have to decide the values of a design variable so that the performance variable do not exceed the limit defined limit. Next is relations of variables for finite length hydrodynamic bearing, that is the Remode and Boyd method we are going to listen here. Remode and Boyd solve the Reynolds equation on computer by using iteration technique. They combine different design and performance variables to form the number of dimensionless parameters. The values of these dimensionless parameters are available in the form of charts and table. These charts and tables are available for full as well as partial bearing. Journal bearings of L and D ratio 1 by 4, 1 by 2, 1 and infinity available. Design and performance variable. First dimensionless parameter is Sommerfeld number or bearing characteristics number. It is defined as S is equal to R upon C bracket square into mu ns upon P. This is the most important parameters. Why it is most important parameter? Because it contains all variables which are controlled by the designer. So it is most important parameter. You have to learn that simple Sommerfeld number. S is equal to R upon C bracket square into mu ns upon P. Second dimensionless parameter is length to diameter ratio L upon D. Next, minimum film thickness variable that is HO upon C. Next, eccentricity ratio that is epsilon is equal to E upon C. And we already seen this equation that is HO upon C is equal to 1 minus epsilon. Coefficient of friction variable or CFV is equal to R upon C into coefficient of friction that is small f. Flow variable FV is equal to capital Q upon RC NSL. Flow ratio QS upon Q. QS is the side leakage or side flow. Next is maximum film pressure ratio that is the P upon max. Position of position of maximum film pressure or maximum film pressure angle, it is the theta P max. This gives angular position of maximum pressure in a fluid film. Zero pressure angle that is the theta P0, it gives terminating position of a high pressure fluid film. Position of a minimum film thickness or minimum film thickness angle, it is phi. It gives an angular position of minimum fluid film thickness. Temperature rise variable that is rho Cp delta T upon P, and all should be SI unit. So this type of tables for the dimensionless parameters for full journal bearings are available as Remude and Boyd perform iteration technique for the dimensionless parameter also, and according to that design and performance variable. So L and D ratio is there, H upon C epsilon Sommerfeld number R upon C into F, Q upon R C N S L, QS upon Q, P max upon P, and according to L and D ratio we will get another meters. Next, in design consideration, temperature rise in finite length hydrodynamic bearings with feed lubrication. In feed lubrication, cool and clean lubricating oil is fed to the bearing from external source. In hydrodynamic bearing, the power lost in friction is converted into the heat, which increases the temperature of the lubricating oil. In feed lubrication bearings, this heat is dissipated by conduction, convection, radiation, and carried away by the flow of lubricating oil. As it is difficult to calculate the rate of heat dissipation by all these methods, that is the conduction, convection and radiation, it is assumed that the total heat generated in bearing is carried away by the lubricating oil. So total flow of lubricating oil. In analysis of temperature rise, it is assumed that total flow of lubricating oil is responsible for the total heat dissipation, and the total flow Q comprises of two parts, that is the circumferential flow due to the relative motion, it is denoted by the QC, and axial flow or side leakage denoted by the Q with suffix X. So first we will see circumferential flow due to the relative motion, that is Q suffix C. The major portion of the lubricating oil flows in the circumferential direction and is present in bearing for the maximum possible duration. This portion of the lubricating oil absorbs the heat, during which the temperature increases from initial temperature to final temperature T1 to T2. So the temperature rise we will get here for the circumferential flow T2 minus T1, that is the delta T. Now axial flow or side leakage Q with suffix S. Some portion of a lubricating oil is constantly leaking through the ends of the bearing, and this is known as an axial flow or side leakage. This portion of a lubricating oil is not present in a bearing for maximum possible time. Axial flow takes place at an average temperature, that is the T average. See here, delta T and T average are both different things. Now T average is equal to T1 plus T2 divided by 2. Temperature rise in axial flow, that is the T average minus initial temperature. T average minus initial temperature is T1, and T average is equal to T1 plus T2 divided by 2 minus T1. So rearranging the terms, we will get T2 minus T1 divided by 2. So it is delta 2. Rate of heat generation, Hg. So power loss in friction is equal to frictional torque into angular velocity. After putting the formulas for the frictional torque and angular velocity, we will get the power loss in friction is equal to 2 pi ns into Fwr divided by 10 raised to 6 in kilowatt. Next is rate of heat generation. Obviously, rate of heat generation is equal to power loss in friction. So Hg is equal to Pa. So we will get the same equation for the Hg uh, as for the loss. Next, rate of heat dissipation, that is the HD. Rate of heat dissipation, first of all we will see all the parameters involved in the rate of heat dissipation equation. Small m is total mass flow rate of a lubricating oil. M with suffix C is the circumferential mass flow rate of the lubricating oil. M with suffix S axial mass flow rate. Cp specific heat, delta T temperature rise, rho mass density, Q total flow rate, Qc circumferential flow rate, and Qs axial flow rate. So mass flow rate of lubricating oil is equal to rho into Q upon 10 raised to 9, while mass flow rate for the circumferential flow is equal to rho into Qc, that is the flow in circumferential direction divided by 10 raised to 9, and for axial mass flow rate it is rho into Qs divided by 10 raised to 9. So rate of heat dissipation HD is equal to, it combines both heat carried by the circumferential flow and heat carried by the axial flow. So it is mccp delta T plus mscp delta T by 2. So substituting equation and rearranging term, you will get the equation for the rate heat dissipation. Next is the temperature rise delta T. As rate of heat generation is equal to rate of heat dissipation, and substituting both the equation for the Hg and Hd, you will get equation for the delta T is equal to 2 pi ns into Fwr divided by rho Qcp into bracket 1 minus 1 half Qs upon Q into 10 raised to 3, and it is in Celsius. Now, viscosity of lubricating oil. In order to simplify the analysis, it is assumed that the viscosity of lubricating oil remains constant as it passes through the bearing. But in reality, what is happening? As the lubricating oil passes through the bearing, its temperature increases and hence viscosity decreases. As the analysis is based on the constant viscosity, as already we studied the assumption of the Reynolds equation, the viscosity should be determined at effective temperature of lubricating oil, and this is the most important point, that if viscosity is not given in numericals, then you have to consider the effective temperature, and for that effective temperature you have to find out the viscosity, and then you have to continue for the design numerical. So the effective temperature of lubricating oil is given by T is equal to T1 plus 0.8 delta T, and average temperature T average is equal to T1 plus delta T by 2. Thank you for listening.